we are hitting a wall, a really fundamental physical barrier in the digital age. For decades, the engine of modern computing has been Moore's law, this relentless, exponential shrinking of transistors on a chip.
Right.
But that engine is stalling. We're now building chips below the 3 nanometer node, and electronics are running right into these fundamental limits.
That's absolutely right. The issues we face are, well, they're deeply rooted in power consumption and quantum physics.
Okay.
When clock frequencies push into the gigahertz range, the power needed to switch those tiny transistors, it just goes up dramatically. We call this the power wall.
The power wall.
Yeah, it's driven by this overwhelming heat generation that makes further scaling just impossible without, melting the chip.
And mathematically, this is a brutal relationship, isn't it? The standard electronic power consumption has a cubic relationship with the clock frequency.
Right. Precisely. To make that visceral for you, if you try to double the speed of an electronic transistor, you need 2 cubed, or 8 times the power.
8 times.
It's a completely unsustainable path for data centers. And on top of that, down at that sub-3 nanometer scale, quantum uncertainties start messing with electron behavior.
Which means they're less reliable.
Exactly. You get reduced predictability in the transistor's fundamental job, which is just to switch on and off.
Okay, so if electrons are failing us because of heat and, physics, we need a truly radical alternative because the world demands more computation, not less. What's the leap?
The necessary leap is integrated photonics, using light, or photons, instead of electrons to carry and process information.
Right.
Optical signals travel within these microscopic waveguides 1 to 2 orders of magnitude faster than electrons fighting their way through complex copper circuits.
And here's the crucial part, right? The power.
This is the crucial difference that bypasses the power wall. Photonic power consumption scales only linearly with frequency f.
Which means if you double the speed, you only need to double the power, not multiply it by 8.
Exactly. That is the definitive advantage we need.
So what does this all mean for you, the listener? We are embarking on a deep dive into the essential role of photonic integrated circuits, or PICs, in navigating this transition. Our mission is to understand how these microscopic light engines are accelerating today's massive AI models and ultimately driving the foundational components for the next technology wave, the quantum revolution.
The transition isn't theoretical, it's urgent. The computational hunger of AI is just insatiable.
I mean, the numbers are just staggering.
Consider the sheer scale. Training the 175 billion parameter GPT-3 model required an estimated 1,287 megawatt hours of energy.
That's enough to power hundreds of homes for a month, just to teach one model.
Just for one model.
And as these models get larger, we're already moving toward these complex trillion parameter mixture of experts or MOE architectures. The constraint isn't the speed of the individual processor anymore, is it?
No, not at all. It's the surrounding infrastructure.
Right.
The bottleneck is shifted away from the silicon compute core itself. Scaling complex AI is now primarily limited by 2 things in the data center.
Okay, what are they?
Interconnect bandwidth and the I/O port count, often referred to as radix.
So how fast you can get data in and out?
Exactly. You can have the world's fastest processor, but if you can't feed it data fast enough across the thousands of chips in a cluster, the chips just sit idle. They wait. They starve.
This is where we see photonics making its first and most immediate impact then, solving that interconnect crisis.
It is.
And a stunning example came from the company Light Matter. They announced a breakthrough that fundamentally changes how much data we can push through existing fiber optic lines.
They demonstrated a 16 wavelength bidirectional, dense wavelength division multiplexing, or DWDM optical link.
And this was on existing fiber.
Just a single strand of standard single-mode fiber.
Yeah.
And with that, they achieved an unprecedented 800 gigabits per second bidirectional bandwidth per fiber.
16 different colors of light traveling both directions at the same time on one thin strand of glass. To put that in perspective for you, 800 GBPs is roughly 800 times faster than the premium high-speed fiber internet you might have at home. This is critical infrastructure, not desktop speed.
And this wasn't easy. Historically, commercial bidirectional transmission, it was often limited to only 2 wavelengths per fiber. There were just too many technical hurdles.
So what do they have to solve?
Well, Light Matter had to overcome massive technical challenges. Things like managing complex wavelength-dependent propagation, mitigating crosstalk.
Which is when the colors of light bleed into each other.
Exactly, they confuse the signal. And they had to robustly handle backscattering and polarization issues inherent in using this, ubiquitous, cost-effective standard fiber. That level of spectral density is the only way hyperscale AI infrastructure can continue to scale.
Now we move beyond just connecting chips to using PICs for the computation itself. The goal here is to offload the heavy lifting from electrons to light.
Right, giving us brand new digital and analog solutions.
Let's start with digital.
Okay, so for digital, we can build basic logic functions, not ND or XR, using what's called electro-optic, or EO, digital logic directly on the PICs.
And these use microscopic structures.
They leverage components like Mach-Zehnder interferometers, or MZIs, and micro-ring resonators.
Wait, Mach-Zehnder interferometers? I mean, that sounds incredibly complicated. How does that function as a basic logic component?
Yeah, it sounds complex, but you can think of the MZI simply as a very precise optical light switch that's controlled by electricity.
A light switch, okay.
Exactly. We split a single light beam into two paths. By applying an electrical signal to one path, we slightly change its refractive index, which effectively speeds up or slows down that beam.
I see.
When the two beams recombine, their phase difference dictates whether the light interferes constructively, which gives you a full signal output, or destructively, which gives you no signal output.
And that light or no light state is your 1 or 0.
That's your 1 or 0, performing the logic function at the speed of light.
That's genius. And this leads us to something called the Electrics Photonic Arithmetic Logic Unit, or EPLU architecture.
Right.
And here, wavelength division multiplexing WDM is used inside the chip for calculation, not just for communication.
Absolutely. WDM is key to boosting the parallel processing capacity. A fantastic example is in a complex operation like addition, specifically within what's called a carry select adder.
Okay, so the speed of addition is often limited by waiting for that carry bit to propagate from one column to the next.
Yes, like waiting for the computer to figure out if it needs to carry a 1 bit before it can determine the next digit.
A familiar feeling from grade school math.
Exactly. The EPLU sidesteps this delay. It computes two possible outcomes simultaneously and instantly. One outcome assumes the carry-in is 0, and the other assumes the carry-in is 1.
And it does this with light.
It encodes these two distinct parallel computations onto two separate wavelengths of light. Once the actual carry bit arrives, the BIC instantly selects the correct wavelength, the correct outcome, with minimal latency.
That efficiency gain is massive. But does that add a lot of complexity? I mean, when you have to recombine or decode those multiple outcomes.
It does. It adds complexity to the circuitry, which requires extremely tight control over the optical paths. But the trade-off is often worth it.
Why is that?
Because the time saved by instantly resolving that carry bit, it dramatically reduces the overall latency in a high-speed arithmetic operation. We're basically trading space and manufacturing complexity for pure processing speed.
Let's pivot now to analog computation, which brings us to the ultimate comparison, the human brain. Traditional digital computing is so energy intensive, but the brain performs an estimated 10 to the 18 multiply accumulate operations per second while consuming only, 10 to 20 watts?
It's an incredible benchmark.
And
Optical neural networks, or ONNs, are attempting to harness that analog efficiency for AI acceleration.
so to mimic the brain, ONNs have to program synaptic weights.
Yes. Which means precisely modulating the optical components to perform matrix multiplication in the optical domain. And we use two main mechanisms for this weight programming. The first is thermal tuning.
Which involves literally heating up tiny waveguides.
Yes, using microheaters to change the waveguide's refractive index. Thermal tuning is highly adaptable. It can induce large changes, allowing for strong modulation.
Oh, what's the catch?
The drawback is its speed. It's limited to low speeds, usually just a few hundred kilohertz. It's also volatile, requiring continuous milliwatt level power. And all that heat introduces the risk of thermal crosstalk.
Where one component's heat messes with its neighbor.
Exactly.
So high adaptability, but it's hot and slow. What's the faster option?
That would be field effect tuning, typically achieved through carry depletion or injection. This method is CMOS compatible and achieves gigahertz level tuning speeds. Yes, up to 50 gigahertz has been reported for some modulators. And because it relies on electric fields shifting carriers, the depletion mode operation offers significantly lower static power consumption. It's fast, integrated, and efficient.
But what if you have a static model where the weights stay fixed? You don't want to waste continuous power just holding that state.
That's where the cutting edge comes in. Non-volatile modulation using phase change materials, or PCMs.
Okay.
By switching these materials between amorphous and crystalline states using a heat pulse, you can program the photonic device statically. The state just sticks around without needing continuous external power.
So it's perfect for those energy efficient static programming tasks.
Precisely.
Okay, so the components are fast, they're efficient, they're versatile, but individual speed is, well, it's irrelevant if the system can't be integrated compactly and energy efficiently. We have to talk about the colossal challenge of integration itself.
And this challenge is precisely why Moore's law scaling is forcing the entire semiconductor industry toward heterogeneous integration, or HI.
Also called system in package.
Right. HI is the necessary engineering pivot. Since we can't keep shrinking the transistor, we have to combine separately manufactured components, photonics, electronics, memory, sometimes even MEMS, into a single enhanced package. You have to combine the best of different material technologies.
But even with that sophisticated integration, what are the three biggest headaches limiting PIC scalability?
Well, the first one is just area density. Optical elements are inherently micron scale, which is significantly larger than nanometer scale transistors.
So light is fast, but it takes up too much physical room.
In a way, yes. This size difference limits integration density. In complex systems, like those MZI meshes we mentioned, the complexity and component count can increase quadratically with the required matrix size. That quickly limits how much we can practically fit onto a chip.
And the second issue is power. If light is the answer to the power wall, I'm genuinely surprised that energy consumption is still one of the top constraints.
That's a great question, and it speaks to where the real energy drain is hiding. The major bottleneck isn't the optical computation or transmission itself.
So where is all the power going?
It's the conversion. The conversion between the electronic and photonic domains. More than 80% of the total system energy can be consumed by data movement memory costs and the signal conversion that happens in analog to digital and digital to analog converters, your ADCs and DACs.
So we can compute with light for nearly free, but we spend huge amounts of power just to translate the data into light and then back into electrical signals.
That's the problem. We just move the power wall to the interface.
And what's the third issue? This one deals with signal quality, right?
That's noise and precision loss. Analog computing, including optical, is inherently susceptible to noise and limited by the achievable precision of its components.
Can you give them an example?
Sure, here's a startling one. Performing a common operation, like a length 32 dot product computation with just 4-bit weights and activations, ideally requires 13 bits of precision for the output result.
13 bits needed. What's the reality?
The reality is that affordable, high-speed ADCs that are compact enough to be integrated are typically limited to about 8 bits of precision.
Oh, wow, that's a huge mismatch.
It's a massive precision mismatch. Trying to encode 13 bits of information into an 8-bit signal, it leads to accumulated errors that just explode into inaccuracy when you chain calculations across thousands of layers in a deep neural network.
It's like trying to build a complex financial spreadsheet with a calculator that only keeps whole numbers.
That's a perfect analogy. The small rounding errors quickly compound until the final result is completely unreliable. And this is a unique challenge that pure digital electronic systems don't face in the same way.
So if PICs are solving today's AI bottlenecks, let's look ahead to where this technology is ultimately taking us. And that destination is quantum information science.
Ushering in what many call the second quantum revolution. Absolutely.
This is the big leap.
Integrated photonics is emerging as the single most compelling platform for this next generation shift. Think about the current state of quantum experiments today.
Right, they're huge.
They often involve complex, large, room-sized arrangements of bulk optical components. Hundreds of mirrors, lenses, and filters, all meticulously aligned on these vibration-dampened tables.
And the goal of quantum PIs, or QPICs, is to replace that fragile, room-sized lab with a monolithic, millimeter-scale chip that does the same thing.
That is the ultimate ambition. QPICs offer significant advantages over bulk optics, most notably providing far more precise control of phase and polarization with vastly higher stability.
And that stability is everything for quantum.
It's critical for manipulating the fragile quantum states of single photons. And QPICs allow us to integrate all the fundamental building blocks, photon sources, modulators, single photon detectors, into robust single packages.
So we need light sources on the chip that can generate single photons. Does standard silicon help here, or do we need new materials for that?
Well, standard silicon is surprisingly useful as a foundational material. Silicon exhibits a high third-order nonlinear coefficient, often denoted as Chi3. And this is a property we exploit to implement on-chip single or entangled photon sources. We do this through optical processes like four-wave mixing, or FWM.
So what's happening there?
Essentially, we pump a strong laser into a silicon waveguide, and that Chi-3 property allows the silicon itself to act as a catalyst, generating pairs of quantum entangled photons through the light interaction.
So that the silicon itself makes the quantum photons.
In a way, yes.
Yeah.
It's a crucial, scalable step toward miniaturizing quantum functionality.
So we've tracked this journey from electronic silicon hitting the power wall to PICs stepping in to accelerate massive AI interconnects in computation, and now mapping a path toward integrating the building blocks of quantum systems onto a single chip. It's an incredibly rapid timeline of innovation.
It is, but the work is ongoing.
Yeah.
There is no final victory until we solve integration completely. Continuous efforts are critically needed, especially in cross-layer co-design.
Getting the software and hardware to talk to each other.
To talk to each other intelligently, yes. And developing advanced integration methods like flip chip bonding or monolithic integration to tackle complexity and that pervasive issue of heat dissipation.
So at the end of the day,
Photonics needs to find the specific niche where it provides a definitive, unassailable advantage over its electronic counterparts.
and if all those integration challenges are solved, what kind of performance are we really talking about?
If the PIC scale can be successfully aligned with the complexity of the computational tasks, and if we can realize those highly efficient electro-optic interfaces, which is the hardest part, then operation at a rate of one matrix vector multiplication, or MVM, per nanosecond could be achieved
Per nanosecond.
in high-throughput applications. That performance is transformative for future AI.
That potential performance gain brings us back to the ground truth of engineering and material science. As you consider this leap from room-sized quantum labs to millimeter-scale chips, remember that the critical role isn't just the light itself. It's the engineering challenge of how we build and package the system. That's a silent battle.
The ability to integrate vastly different materials, specifically materials like 3V semiconductors, which are necessary because silicon cannot efficiently generate laser light onto a CMO-compatible silicon platform. That is the silent battleground determining whether this photonic revolution will truly succeed. It's a material science war we have to win.